In the name of Allah, the most gracious, the most merciful, all praise is due to Allah, and peace and blessings be upon the messenger of Allah, our master Muhammad, and upon his family and companions altogether. Now, as for what follows, by time indeed mankind is in loss, except for those who have believed and done righteous deeds, and advised one another to truth, and advised one another to patience. The national revival is the overcurrent relay curve, TCC curve. If current exceeds 10 amperes, relay trips instantly. Trip time is controlled by adjusting the curve. If set to trip at 5 seconds and current exceeds 10 amperes, relay counts down. After 5 seconds, if fault persists, it trips. If set to 2 seconds, it waits 2 seconds to trip. I setting is controlled by shifting the curve. Manage overcurrent by controlling setting current and trip time. So, if the fault current or the measured current exceeds the I setting value, which is 10 amperes, the relay starts counting down. The timer inside the relay begins to count. If the 5 seconds elapse and the fault is still present, it will issue a trip command. However, if we lower the curve to trip at 2 seconds, the relay will wait for 2 seconds before issuing a trip command. We can control the I setting value by shifting the curve to the right or left. Therefore, we can manage the operating area of this overcurrent relay by controlling two things: the setting current value and the trip time. Now let's assume that the set point current or I setting value is 10 amperes. So we can control the operating area of this overcurrent relay by managing two things: the setting current value and the trip time. Now let's assume that the set point current or I setting value is 10 amperes. The I setting is 10 amperes and the trip time is 5 seconds. So as soon as the measured current exceeds the set value, the relay will give what is called a wake-up signal, meaning it has activated, but hasn't issued a command yet. It will issue a command to the circuit breaker only after the 5 seconds have elapsed. So we conclude that the trip decision is a combination of a pickup plus a time delay. If the time delay value is 0, or if the trip is instantaneous, then as soon as the pickup occurs, the trip will happen. Usually the topic is set so that the trip time is longer than what is present, because if a fault occurs on this feeder, it wouldn't make sense for it to trip before this feeder. If that happens, we say there is poor coordination between the feeders. If a fault occurs on a feeder, only that feeder should trip, while the others that are not affected by the fault should remain energized. If this happens, we say that there is poor coordination between the two. If a fault occurs, only that feeder trips. If it trips, it will cut off the supply to the other feeders not affected by the fault. Discussing the coordination between the main circuit breaker and the feeder circuit breaker, if the setting value for the feeder circuit breaker is 10 amperes, we set the setting value for the main circuit breaker to 15 amperes, e.g. If the trip time for the feeder circuit breaker is 1 second, we set the trip time for the main circuit breaker to 2 seconds. We set feeder values based on cable damage curves from manufacturers. We need to isolate the fault before the cable fails or burns out. The important question here is, on what basis did we set the setting for the feeder circuit breaker to 10 amperes? Typically, we set the value for any feeder based on our prior knowledge of the cable's damage curve, which we receive from the manufacturer. We need to isolate the fault before the cable fails or burns out. I mean, what's the point of isolating the fault after the cable has been destroyed? What's the benefit of the protection that was applied? Thank you. Obtain the cable integration curve from the manufacturer. Ensure the overcurrent relay curve does not intersect and is above the cable integration curve. In the diagram, the black curve is the cable integration curve, and the red curve is, the blue curve is, we have 3 fault possibilities. First, the fault clears, the current passes and burns out. Second, a fault occurs before the intersection, which is safe. Third, a fault occurs with a current exceeding the intersection, causing the cable to burn before the relay operates, which is dangerous. What's the solution? The red curve represents, while the blue curve represents, we have 3 fault possibilities. First, if the fault is cleared, the current burns out, ending the matter. Second, a fault occurs before the intersection, which is healthy. Third, the worst case, a fault with a current exceeding the intersection burns the cable before the relay operates. This is dangerous. So, what's the solution? The second possibility is that a fault occurs on the cable, but at a value before the intersection. This is correct. However, the worst case is a fault occurs on the cable with high current exceeding the intersection, and the cable burns out before relay. So, what's the solution? Use another curve for full cable protection. Note, solving one coordination issue led to another. Here, it operates prematurely, a coordination failure. So, what is the solution? The solution is to use a curve that protects the cable before it burns out. However, solving one issue caused another. In this area, it operates incorrectly. What's the solution? Increase the relay trip time to prevent the overcurrent relay curve from intersecting with the fuse curve. Yet this causes the relay curve to intersect with the cable curve again. To fix this, introduce a new stage to stop this intersection. We are coordinating between the fuse, relay, and cable curve. This needs focus, even for simple circuits. In complex circuits, intersections are inevitable. Preventing all intersections is impossible. So what's the solution? Increase relay trip time to avoid relay curve intersecting fuse curve. Introduce a new stage to prevent intersection with cable curve. Focus is needed, especially in complex circuits where intersections are inevitable. Perform short circuit calculations to find maximum fault current. Intersections beyond this point or at the line's end are not worrisome. If we notice, we are aligning the fuse, the overcurrent relay, and the cable damage curve. This coordination is for a simple circuit and requires focus. However, in some cases, when the circuit is complex, there will inevitably be intersections between the different curves. Even if all the people on Earth gathered to ensure that these curves do not intersect, they couldn't. So, what's the solution? Perform short circuit calculations and find max fault current. If there is an intersection between the curves after the maximum fault current, no worry, faults can exceed max current. So, intersections after max current or line end don't matter. Ensure all protections are set for a different system. The solution here is that we perform short circuit calculations and determine the maximum fault current. If there is an intersection between the curves after the maximum fault current, we don't need to worry about it because it's impossible for a fault to exceed the maximum fault current. So why focus on it? Therefore, we don't care if there's any intersection after the maximum fault current or at the end of the line.
All protective measures must work to create a different system. For example, when a fault occurs here, it shouldn't affect the electronic devices of users in the nearby area. Only the affected area needs to change, so only this relay should operate. This is achieved quickly by the relay in the nearby area. For a different strength, the black circuit will close first before the main circuit moves, so the black chart will close first. So the black chart will close before the main chart moves. Usually the main circuit might wait for years for a fault to happen, but when a plot happens, they have to work straight and fast. But when a fault does occur, they need to operate reliably and fast. They need to operate reliably and fast. But when a fault does occur,
we mentioned that the drawback of the instantaneous overcurrent is that it makes coordination between different overcurrent relays difficult, especially when there are two short and consecutive lines. This is because the difference between the fault currents on those two lines isn't significant, so the relay can't distinguish whether the fault is on its own line or on the other line, which can lead to one of them tripping before the other. It is not recommended to use it even for transformer protection for the same reason, the difficulty in coordination. The goal of having it is to avoid tripping the circuit for any transient fault, because the device will wait for a specific duration before giving the trip signal. So, if the fault is transient, it will disappear before the specified trip time elapses, and thus the circuit won't trip. If the fault is of a permanent type, it will be disconnected after the set trip time expires. One might ask, what if the fault is transient but remains present even after the set time has elapsed? What will happen then? In this case, the relay will incorrectly trip the circuit breaker because this fault has misled the relay into thinking it is a permanent fault when it is actually transient. To overcome this problem, we use what is called an autocloser, which is an automatic reclosing mechanism for the circuit breaker. The purpose of the automatic reclosing is to check whether the fault that caused the trip was indeed a fault or not. The reclosing happens after a specified time period. If it trips again after the reclosing, that's strong evidence that there is a fault. However, if it doesn't trip again, that indicates that the previous trip was a false alarm.
Let's take a look at the open circuit version. As you are using the circuit breaker closures, 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 You are using the circuit breaker closures to now simulate the transient fault on the feeder. Just like you are using circuit breaker closures. Let's now simulate a transient fault on the feeder. The reality will now increase due to the step, and the control motor will take over. We start the control theft. The sky was a deep, endless blue, stretching far and wide, a mesmerizing hue that captivated the senses. Blue, in all its glory, painted the world with a serene and calming presence, echoing the tranquility of a peaceful ocean. Blue, 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 the color of dreams and infinite possibilities. After the fixed time, we reset the protection system. Once covered, incidents clarify. Then we try to cover the station. When the station is covered, the incidents start to clarify again. The time duration from when the station is covered until the incidents start to clarify again is when the station is dead. So we recognize this as dead time, and this is the time from when the station is covered until it is covered again. This is indeed well known for more than just the cancerous motors, and it depends on the design of the cancerous motors and the mechanism used. After the heat starts again, and we don't detect any further steps, we close the closed loop, which returns to its initial state. The difference in time between when the closed heat starts and when the mechanism closes, it is called the closing time. This is the time we achieve to confirm that the organization is correct. A test to confirm that the data is correct. Among them is the renaissance of a nation, the scanning time, the future time, and the future settings that we can use in the changing system,